Hi, today I'm going to talk about how zone namespaces improve SSD lifetime, throughput, and latency. My name is Matthias. I am a director of emerging systems architectures within Western Digital. Right, so let's get started. First, I want to talk about the block interface. What's the block interface? It's the read-write interface that you have when you kind of access your storage devices, where you read logical blocks, LBAs, or you write logical blocks. Initially, this was for hard drives, and later this will apply to SSDs. The idea of this interface is that it hides disk-specific details, how to manage media and so forth, and presents this very general, efficient storage interface up to the host on which they can kind of build its application on top. It has worked and continues to work really well for a multitude on storage systems. But for flash SSDs, the cost of supporting this block interface has become quite high and has grown over time. And the reason for that is there's a fundamental mismatch between the operations allowed, read-write, and our underlying flash technologies operations like read, program, erase. So whereas you can read or write a single LBA with the block interface, with the flash interface, you usually read at a certain granularity, you program at a certain granularity, and you erase at a certain granularity. Furthermore, you can only do this specific number of times. Right. To kick this off, I want to point you to the graph on the right, and where we have compared what we're going to talk about, zone namespace SSDs, and in general, versus a conventional SSD. And for that, we see that when we kind of look at the write throughput, which we're depicting here, and then we kind of say we do a full drive write 2 times. And for the conventional SSD, we have what's known as a 7% over-reasoning and 28% over-reasoning. I'll get back to how that relates to this. And then we have the ZN SSD, which has 0% over-reasoning. And when you write to an SSD the first time, you usually always get really good performance. But when you kind of get to the second drive write, and there's this garbage collection process that kicks in within the SSD, depending on the implementation of the software within the SSD, and depending on how much over-reasoning you have, and so on, for conventional SSD, and you would have like, if you're 28% over-reasoning, you have like 50% lower throughput when you get to the second write. And for when you only have 7% over-reasoning, you actually get like 75% lower throughput. Whereas for ZN SSDs, which we're going to talk about today, we see no drop in throughput. You can have a consistent performance from you begin to write to the drive, and kind of keep going on and on. And these results are based on a pre-production ZNS SSD and conventional SSDs. A conventional SSD platform. It's the same platform for all of the 3 here. The only difference is the firmware between the 3. All right, so to get you a little bit into what an SSD is, I give a little bit of background. An SSD bundles like 10 to 100 these NAND chips, the flash technology, and an SSD controller together. The SSD controller manages the NAND chips characteristics and exposes the storage through a host storage interface, such as NVMe, which typically implements the block interface. Inside of the controller runs this management software, which is often called the flash translation layer. And the reason that we saw here before with the throughput drops, I'm going to take you through why that happens. So for data placement on conventional SSDs, take this example to the right where you have 4 files, A through D. They write it into a file system, and when they go into a conventional SSD, it typically has an erase unit that it writes into. An erase unit is effectively a set of flash blocks, which you must write sequentially to. They wear out. You can only write to them a certain number of times, and whenever you want to kind of get to the next part, they must be erased before you can kind of rewrite. It's the erase part that kind of says how many, known as how many times you can erase. So one of the responsibilities of this the flash translation layer is to map this very simple interface, block interface, read-write, the logical blocks onto the physical addresses of the media. And what typically happens is that these four files, when you write them down, is that they don't have the same lifetime. One of the files might be a temporary file, so it might only use 5 minutes, while all the data that you wrote at the same time might stay there for days, weeks, years, months or years. And in that case, well, what happens is that at some point it needs to be garbage collected to free up new space. And since we can only write sequentially within this erase unit or set of flash blocks, we have to clean up another flash block to kind of enable that. And that's called garbage collection process. And when it has done its thing on a single erase unit, then you can kind of rewrite and write to it again. So what that means is that within the SSD, the conventional SSD, it rewrites data. So data you wrote once from the host point of view kind of gets into the SSD and gets rewritten multiple times. That is known as the write amplification factor. The best write amplification factor you can have is 1x, where you write the data once from the host to the drive and it's only written once. But for conventional SSDs, very often the write amplification factor is much higher. And what this leads to is lower write throughput, higher read latencies, because you're writing more and that impacts the read latencies. And it also has a higher dollar per gigabyte cost due to the overhead of the flash translation layer in general. And this write amplification factor occurs due to this mismatch between the block interface and the SSD's media interface. So the cost of this is, when you look at it from the flash translator point of view, there's two things. One is the media over-provisioning, which improves performance, but it increases dollars per gigabyte. So where you say, and it has like directly related, if you have very little over-provisioning, like 7%, you can see out here to the right for this particular workload, we've shown RocksDB override workload, where 7% you have a write amplification factor of over 2.5. If you have 28% over-provisioning, you have slightly above 2, and if you have more than twice the media, you always have an opportunity to kind of find a flash block without any valid data in it. You kind of get this write amplification factor. But the key is that you actually have to pay for that media to get that extra performance, and you don't get to store your own user data. The garbage collection process within the SSD solely uses it for your own purposes. The other thing is you have 1 gigabyte of mapping table that you manage, this logical block until the physical media mapping table. And it usually uses 1 gigabyte per 1 terabyte of media. And typically for enterprise SSDs, this is stored in DRAM, which to get the best performance. So, it improves the performance, but it increases also the dollars per gigabyte. And it is such that the media and DRAM are often the bulk cost of an SSD. So the idea of ZNS and Zone Namespace SSDs is that can over-provisioning and DRAM be significantly reduced while we improve the throughput, latency, and dollars per gigabyte? That's the question. And that's what it does. So with Zone Namespace ZNS SSDs, it enables the host and the storage device to collaborate on data placement. The host software stack has to naturally write sequentially within an SSD's erase unit. What this does is that it eliminates the write amplification factor of the SSD's garbage collection process. It eliminates the conventional over-provisioning. It needs less DRAM due to a smaller mapping table. Since you're writing sequentially, you don't need to have what's known as the fully associative mapping table. You can have a more coarse-grained granularity mapping table. And also, while doing that, you can have higher throughput and lower latency. And how much you're saying? Well, as we saw early on, the conventional SSD 7% over-provisioning maxes out at 236 megabytes per second, where the ZNS SSD continued to kind of be able to write at a higher throughput. So we show here that for a ZNS SSD, where a conventional SSD would drop off at 236 megabytes per second, a Xeon SSD is actually able to sustain 4.6 more writes per second than the conventional SSD is able to. And so suddenly you can write much faster to an SSD. You get consistent write performance. But also, how does this impact our latencies? So for the latencies, we have this example. We saw before that the conventional SSD were only able to sustain these around 236 megabytes per second. So let's see what is the latency impact if we, while doing writes, we also measure the read latency of a single 4K random read at QDEF1. So at that point, what we do is that we start out with no writes going on, just reads, random reads. And in that, first thing we want to note is that the pre-production ZNS SSD has slightly lower performance throughput latency, whereas a conventional SSD is slightly higher. And that's only due to the firmware maturity of the pre-production ZNS SSD. Production ZNS SSD would have the same average read latency. And then as we kind of add writes, like 25 megabytes per second, let's say 50 megabytes per second, like a 95.5 random read write workload, what we see is when we compare it to the ZNS SSD that goes down here, and we have the conventional SSD, we are actually 12% better, like average latency, than the conventional SSD. Similar, if you go to our 9010 random read write workload, we have 29% better average latency. And when we go to a typical 8020 random read write workload, we actually see 50% improvement in average latency. So there's a huge, as there are some writes going on, which typically is in an SSD, you will see significantly improved average latency from your IO workload. All right. So there's a lot of benefits to this, and to make all this happen is kind of where we have this new specification. So the Zone namespace command set specification is a new command set that's been added into the NVMe Express organization. Was released back in June, and what it does, it introduces the ZoneStarts model, the introduction of zones and their associated behavior, the Zone namespace types inside of NVMe, which supports this model, and the Zone namespace command set, where this namespace support exposes these new commands. There's like zone management receive, zone management send commands, and why you can still do like read and write and so on. And early on, we had, like before this specification, there was a big movement in the industry to move to kind of like have this collaborative data placement. And with this new specification, we are now having a standardized interface to perform data placement, collaborative data placement between the host and the device for NVMe devices. All right, so the ZoneStarts model, just to give you an overview, so we set that in a erase unit. You had to write sequentially. You can think of a zone mapping to an erase unit within the SSD. Zones are laid out sequentially in an NVMe namespace. So you have zone 0, zone 1, so on, and then there's a set of LBAs within each zone. The zone size is fixed, which means each zone has the same number of LBAs per zone, and applies to all zones in the namespace. For example, they can all be 512 megabyte size. Since we are in SSDs, and particularly for flash media, it's not always that you have a zone size, for example, be a power of 2. So what we added into ZNS is there's this zoned writable capacity, which kind of defines maybe you can write 512 megabyte. The zone size is 512 megabyte. The writable area is 500 megabytes. And then around these zones, there are rules in how you can read them and write them. And the great part about the ZNS command set is that it builds upon and inherits the commands from the NVM command set. So you can still use your flush command, your read command, write command, and so on. It's just when you write to the media, there are certain rules that you have to respect when you're writing to it. So when you write to a zone, it must be written sequentially. It's called sequential write required. And if you want to write to it again, you have to reset it. Issue this zone reset command, which is done through a zone reset action, which is done through the zone management send command. Each zone has a set of associated attributes. For example, write pointer that points to the next place to write sequentially. The zone starting LBA that points to the first LBA. The zone capacity, which is the writable area within the zone. And the zone state that defines the read-write access rules. And this process, I mean, so the ZoneStarts model is actually for ZNS, and so namespaces is very similar how it is for SMR hard drives. So one of the things that we did when we wrote this specification within the NVMe organization was to make sure that we aligned the SMR interface specifications, SAC and CBC and T10 and T13. We were very particular about making sure that those 2 or 3 specifications kind of had the similar ZoneStarts model, which means that you very likely can use the same source. You can use the same software stack for SMR hard drives as you would for ZNS SSDs. With small, where ZNS SSDs has the zone capacity where SMR hard drives does not. So you can always write to the full zone size within a SMR hard drive. It might not be the same for a ZNS SSD. Then we have, I told about, there's these zone states which control what you can do. And there are like this state machine that works when you write to a zone is empty. There's no writes to a zone. You can be ready to write to it. When you write to it, it goes into an implicitly open state. And if you explicitly open it using a zone management send command, it goes into explicitly opened, but let's keep it simple. And then as you write to it, you can read to it. You can read data before this write pointer. Obviously, but you haven't written the data yet. So if you try to read outside of the write pointer, you will get either read error or you will get like just predefined data back. It depends on how the error recovery feature within NVMe is configured. It's orthogonal to how CNS works. And then when you've kind of written all the writable LBAs within the zone, it transitions to full. And then if you want to transition it from full to empty, you issue this zone reset action using the zone management send command, and then you go back to empty. That's it. Right. So for reading from a zone, whereas writes are required to be sequential within a zone, reads may be issued to any LBA within a zone and in any order. There is one caveat, and that is that if the zone is in this offline state, which means that it's basically offline, you're not addressable, you can neither write to it or read to it, then that would result in an error. But for any other zone state, you can kind of read any other zones that are in any other zone states, you can read the data in any order that you like. So you only have to think about ZNS when you're writing to it. When you read, you can do it in any order and size as you like. All right. So I talked a little about SMR hard drives, and it implements the SMR, SAC, and CBC specifications. Those are there, and you have ZNSDs which implement the NVMe zone namespaces command set specification. And we worked really hard in the standards group to align to the SAC and C specifications to allow interoperability, which means we have a single unified software stack that supports both software types. And some of the work that we've been working on is to utilize the already mature Linux storage stack that's built for SMR hard drives. So today, when SMR hard drives came to the market, when I talk about host SMR hard drives, what I mean is host-managed SMR hard drives, which requires host software to be managed. For that, we've had support for quite a while, since Linux kernel 4.10. So, and even before that, you can have like pass-through commands. But since this stack has been for SMR hard drives built up many years, it's mature, it's robust, and it's used by many of the biggest global companies today. And therefore, it's already been battle tested. It's there. So for ZNS SSD, what we had to do was just to add on these extra attributes, for example, the writable zone capacity, and then we could effectively already have a mature storage stack. So we did that. We also added in support into F2FS. We are working on BODFS. The Damien Demol has developed ZoneFS, which allows you to expose zones as files up to the host system. We added in support to DM zone, DM linear, DM flaky, and so on. And furthermore, so there's the Linux kernel, which is one data path and how you get to a CNS drive. SPDK also recently got support in the 2010 release. So now you can also use SPDK with CNS drives. It has support for the zone management, send and receive command, and support for identifying, reporting zones, zone reset actions, and all of that is supported today. Which means you not only have the Linux kernel, the Linux kernel storage stack, you also have the SPDK storage stack. If you use that as your kind of your storage backend, and as a storage backend to communicate with your devices. We also worked a lot on tooling. So FIO has support today, NVMe CLI, and libcbd. libcbd is a continuation of a library called libcbz, which were specifically for SMR hard drives. libcbd kind of sets the pass-through commands of before, like kernel 4.10, and now is the library you can go use when you develop ZoneStarts applications that want to implement support for those devices. We have block test where you can test the zone block devices, and we have added in support to util Linux as well. There's this block zone utility, so when you go in and want to report zones, there's already like a block zone command inside of the most Linux distributions, of which you can actually just report zones, reset zones, and so on. There's applications. We have RocksDB, which we are currently in progress of enabling, where we have the ZenFS as a new storage backend for RocksDB that Hans Holmberg has been working on. You can see his SDC presentation below. We are planning MySQL support. HHSE is a Micron project, which is also planning ZNS support. We have Ceph, which we're also planning. We have pushed some patches and still working on it. And the same for HCFS. We're also planning ZNS support and in general zone block device support. So even if I say ZNS, it means in general ZoneStarts support. So this works both for SMR hard drives, but also for ZNS SSDs. It works together. All right. So to make all this kind of easier and to adopt and use, we've launched ZoneStarts.io. It's a kernel community site, which kind of defines the Linux kernel features from rich version, system compliance tests, Linux distribution support, application and libraries, benchmarking. How do you get started? How to get going? I mean, everything you kind of need to get going with ZoneStarts devices. So the summary: as ZNS SSDs, you collaborate on data placement, you improve your write throughput by over 4x, your read latency by 57% or more in an 80-20 random read-write workload. You have lower dollars per gigabyte because we reduce the overreasoning and the DRAM requirements of the SSD. It's fully standardized in the NVMe Express organization, and it's right now it's available as a standalone specification, and it's easily adopted through the existing Linux software storage stack. The storage stack, I mean, we have already quite a few kind of both the base with the Linux kernel SPDK, we have the tooling, and there's more applications, and there's more that's kind of been worked on by everyone kind of the community in enabling it. Thank you, and have a great day.